faces are showing up. Okay, here we go. So what I'd like you to do now is choose for each of these problems, what are the critical numbers? Notice that I just did all the hard work. I gave you the function and I gave you the derivative in factored form. So all that messy algebra stuff that we did before, I've already done that for you. Now I just want you to identify where the derivative is 0 or where the derivative is undefined. When you're done, if you would send that to me in the chat, please, so I know that you're done. So send me what your answer choice is for those, and then if you want, go ahead and keep moving down the document. So let's go ahead and take a look at number 2 here. Notice that we've got critical numbers when the derivative is either 0 or undefined, as long as they are what type of points? Interior points. So k prime. So k prime of 3/2, if you were to plug 3/2 into the derivative, you would get out 0. And k prime of 0 is undefined. Now both of these were interior points, so those are both critical numbers. Okay. What do I mean by I said interior points? I should have done this from the get-go. What was the domain of k from the get-go? The domain of k went from -infinity to infinity. And so sure enough, both 3/2 and 0 are interior points. And so there we have the critical numbers. All right. Now, most folks got the second one incorrect. Okay, let's take a look at that. So certainly, well, let's go ahead and do the first thing. What's the domain of j, folks? What am I allowed to plug into this function? And my guess is if you guys had paused to write out the domain of j, then you wouldn't have the error on it. What's the domain of j?
-5 to infinity.
No. Folks, what do we need? We need the expression in the square root. It's a good guess, folks, but we need the expression inside the square root to be what? Greater than or equal to 0, right? Which means we need... Oh, I'm a liar. I'm sorry. I was thinking about another problem for later. I'm sorry. Both Marshall and I think it was Daniel were correct. I'm sorry. I'm such a liar, but let's go ahead and finish it out anyway. We need this to be greater than or equal to -5, so the domain goes from -5 to infinity. I'm sorry, folks. On the next page, I switched that around on you. So, sorry about that. Great. So there's our domain. So, when is the derivative 0? Well, j prime of 0 equals 0, and j prime of -4 equals 0. That's where the derivative is 0. And what is j prime of -5, folks? It's undefined, right? Anyone have any questions on that? Okay. But which of these are critical numbers? Only x equals 0 and x equals -4 are critical numbers. If I were you right now, I might have a question. I'd go ahead and ask it, because I'd probably have the same question.
So -5 is in it.
Yeah, so what's the issue? -5 is a place where the derivative is undefined, right? The original function was defined there. The derivative's not defined there. But what's the rub? What's the whole point of this example?
Not interior?
It's not an interior point. It's a boundary point. And so -5 is not a critical number, since it's not in the interior of the domain of the original function. And so our only two critical points for this are 0 and -4. Folks, I kind of wanted you to step in this. The most common wrong answer for this was to say C, that it was 0, -4, and -5. I kind of wanted you to step in it so that now you'll watch out for it. Okay. Now, you're less likely to make the mistake if the first thing you do is identify the domain. Okay. So I'm going to let you guys on your own time fill in number 4 and number 5. Okay. But it's what we just talked about. And instead what I'd like to do is I'd like to get you guys to go ahead and jump into number 6 here, and I want you to find all the critical numbers of this function. The work here is almost identical to the work that I did up here. So just mirror your question number 1. Mirror that question number 1. And we'll check in just a minute. Okay, folks, I recognize that probably wasn't enough time to get the problem done. But at least it got you thinking about it. So the domain here of the original function f is what?
Negative 1 to 32.
Oh, yes. Yes, it is, right? Careful there. Why? Because I told you the domain is negative 1 to 32. That's really important, folks. Because if we're going to go looking for extremum, we need to identify our domain correctly. Very good. Got to get up pretty early to make fewer mistakes, or make more mistakes than me in a day. All right. So that's our domain. Thank you, thank you. And now we need to go find the critical numbers. Well, to do that, we better find the derivative. Okay, well, it's a product rule just like before. Here's the first times the derivative of the second, plus the second times the derivative of the first. Now we got some messy algebra. Folks, you get some opportunities to practice it. If at home all you do is look over these notes, you're not going to get good at this algebra. You have to do it. You have to rewrite it yourself. Here we go. This gives me negative x to the 3/5 power. Plus 3 times 8 minus x all over 5 to the 5x to the 2/5 power. Okay. Where all I did on that right-hand side was I did some rearranging with the numerators and the denominators. The big thing was I took the factor of x to the negative 2/3. I took it below the line as x to the positive 2/3. So now we need to get a common what, folks? We got to get a common denominator here. So I'm going to multiply this by 5x to the 2/5 over 5x to the 2/5. That's going to give me that common denominator for that first term. Let's go ahead and distribute that 3 out. So it gives us 24 minus 3x all over 5x to the 2/5. On the left-hand side, we end up with minus 5x all over 5x to the 2/5. Folks, can I cancel those 5s? Well, you're allowed to. Do you want to?
No, then we couldn't add those fractions.
The whole point of putting that 5 in the denominator was so we had a common denominator. And if we start canceling stuff out, we no longer have the common denominator that we're after.
Would it be to the 5x to the 2/3?
I think that it's to the 2/5 here. Great question. The reason why is because the original function was x to the 3/5. And so when we took its derivative, we brought down the exponent, and then we subtracted 1 from the exponent. So that'd be 3x to the 3/5 minus 5/5, which is how we ended up with x to the minus 2/5. That's where that 2/5 factor started showing up.
Excuse me, you have an error then when you took the derivative. You have it written in as 3 over 5x to the negative 2/3.
Oh my goodness gracious. Oh.
You corrected it further down. But...
Oh, thank you, thank you, thank you. Folks, let me highlight that in red there so you can see where the error was. That should be a 5, not a 3. Yeah, I'm telling you, you got to get up awfully early to make if you want to make more mistakes than me.
How did it become positive when you moved it to the denominator? That negative 2/5?
That's by definition, right? So if I have a to the minus 3, by definition, that's the same thing as 1 over a cubed.
Oh, that's in the, I see. It's just, okay, I see. It was just hard to tell where I was looking that it was all in the denominator.
Yep. Yeah, great question. No. I mean, math is all about, I show you one thing that's easy if you're just looking at it in a vacuum, and I show you another thing that's easy if you're just looking at it in a vacuum, and then I put a whole bunch of those easy things together, and all of a sudden, it's a lot to keep track of. Yeah, so completely understand. Great question. Okay, folks, we are almost done with our goal. I can now add these two fractions together. It's going to be 5x to the 2/5. And just to save a little time here, that's 24 minus 8x, where I went ahead and combined my like terms. Okay. And so now we're ready to answer the question, when is f prime of x equal to 0? It's equal to 0 if x equals 3. Does everyone see that? Everyone see where I got that 3 from? If you don't, stop me.
What's that written before x equals 3?
If.
Oh, if. Oh.
Great. And then f prime of x is undefined. If x equals 0. But now we need to confirm. So we found where the derivative is 0. We found where the derivative is undefined. Does that make them automatically critical numbers? No, they also have to be what?
Interior points.
Interior points. And I got a great question. Just to clarify, an interior point is in the domain, but it's not on the boundary of the domain. So for example, here our domain was -1 to 32. If I found that 32 was a place where the derivative was 0, I wouldn't technically count it as a critical number. Or if I found that -1 was a place where the derivative was undefined, I wouldn't technically count it as a critical number. And that's just by our choice of definition. Okay? I think of the critical numbers as a way of saying, let's do a sweep to find all the potentially interesting points on this graph. And the critical numbers sweep those up. Okay? Now, we will address, if -1 was interesting and if 32 was interesting, we will address that, but not as a critical number, but when we check our what?
Endpoints?
When we check our endpoints. So folks, does anyone want to go over that further, what we mean by an interior point? So the interior points would be any point between -1 and 32 on this, but not -1 and 32. Even though they're in the domain, they're considered boundary points, -1 and 32 are. So I wouldn't include them when I talk about my interior points.
I have a bit of a semantic question. So I was aware that I was going to need to use the interval of -1 and 32 like for the problem. But I was still thinking the domain was all real numbers, but we're only looking at the interval. But since it's given in the problem, then that is the domain of this problem?
Correct.
Is that okay to say it that way?
Yes. So if I give you, for example, f of x on its own, or sorry, f of x on its own is equal to x squared, you infer that the domain would be all real numbers. And so its graph would be the graph of this parabola. But if I tell you that f of x equals x squared on 0 to 2, in fact, let's do it just for fun, on 0 to 2, then I've told you that the domain is this, and so then when I'm talking about this particular function, I'm only talking about this piece right here. Great question. Great question. All right, folks. So, because both x equals 3 and x equals 0 are places where the derivative is either 0 or undefined, and they are interior points. Those are our critical numbers. One page done. It only took us 45 minutes. But we're having fun. That's what counts, right? All right. I'm going to do number 7 rather quickly here. It's the same idea. The first thing I'm going to do is I'm going to identify the domain. The domain goes from, here's where I need to be more careful. The domain goes from negative infinity to 5, like so. If you want to see that, you just simply say, what do we want? It sounds like a union chair. What do we want? The radical non-negative. When do we want it? Right now. All right. What do we want? We want the expression inside the square root sign to be greater than or equal to 0. So we set that. We give ourselves what we want, and then we solve for the x. Careful. Remember, when you divide by a negative with an inequality, you reverse the direction of the inequality. So that's how I got the domain of the original function g. Okay. So now we're going to find g's derivative. First times the derivative second plus second times derivative first. Cleaning that up a little bit. We need to get a common denominator here. So we notice that g prime of 0 equals 0, and we notice that g prime of 4 equals 0. Those are the two zeros of the derivative. We also notice that g prime of 5 is undefined. Okay? So folks, what are my critical numbers? Write them out. Please don't say it out loud. Write them out. What are the critical numbers for this function? Correct? Critical numbers of this function are just x equals 0 and x equals 4. Okay. Now, 5 is a place where the derivative is undefined, right? But what did we pause to do before we even started the problem? We identified the domain, and we see that 5 is a boundary point. It's not an interior point. And so our derivative is just our critical numbers are just 0 and 4. Okay. Folks, if you stepped in it the second time, if you thought 5 was a critical number, that's okay. You can step in it twice, but now we got to start correcting ourselves. Okay? All right. I'll let you answer number 8 and 9, or number 9 is nothing to answer. Let's look at number 10 now. This is getting old. But we've done all the hard work that I'm asking you to do. All the hard work's done. Number 10 says find the critical numbers of f on this particular interval. Well, we already found the critical numbers of that function. We already found the derivative of that function, so let me go grab that here. We said that f prime of x, we're on number 10 here. We said that f prime of x was this. And let's just recap. What's the domain of f, folks?
Right, that's just -1 to 1.
Bingo. Bingo. So where is f prime of x equal to 0? It's equal to 0 at x equals 3. F prime of x is undefined at x equals 0. So what are my critical numbers, folks? Everyone identify your critical numbers. Identify all one of them. There's only one critical number here. It's at x equals 0. Yes. It's fun. I can see the wheels turning even though I can't hear what you're saying. Folks, why is 3 not a critical number?
It's not in the domain.
It's not in the domain of the function as what we restricted it to. Okay? Let's see why this is important. Okay? Here I'm asking you to review number 52 from your pre-work from last time. Well, I think that's what we started at the beginning of class with. We just reviewed that. That's our steps for finding the global extremum. Confirm it's continuous, find the critical numbers, throw out any that aren't in the domain. Then this is kind of the key step here, those two steps right there. So let's jump back to it. Let's find the absolute extremum. Okay. Well, first of all, absolute max and min exist. Since f is continuous on -1 to 32. What do I mean by that? So the extreme value theorem applies. Again, if you're going to go looking for a needle in a haystack, it's always good to know the needle's in there. And the extreme value theorem guarantees that we'll be able to find an absolute max and absolute min. Now, where could they be? They could either be at the critical numbers,
How do you know from the wording of the question when you can include the endpoints and when you can't?
How do you know from the wording of the question?
So
Because I included the endpoint there. I'm using that.
But for instance, on a few of the examples above, or on one of the examples above, it was from -infinity to 5, I believe.
Uh-huh.
And 5 was included.
In the domain of the function.
Yeah.
Why? Because what happens if you plug a 5 into this function?
No, I'm saying 5 is included. I understand that, but it's an endpoint. So for Rolle's theorem, we couldn't use it. So how do you know when we're applying Rolle's theorem versus when we're applying the extreme value theorem, which can include endpoints?
Well, Rolle's theorem is kind of a completely different issue. It has to do with finding a place where you have a horizontal tangent line if you have a very specific type of function.
Okay.
And we're not necessarily being tasked with showing that there's a horizontal tangent line, although we kind of do that when we find the critical points. I would just say that, here our domain included 5, but 5 was a boundary point, so when we found that 5 was a critical number, we had to throw it out. And by throwing it out, Andrew, I mean we're not going to call it a critical number, That doesn't mean it might be a location of an absolute maximum.
Oh,
We are going to
okay.
check for that, and that was my pregnant pause that I did just a moment ago when I said, okay, if we're going to go looking for if we're going to go looking for the absolute extremum, they could occur where? Where I have critical numbers
Or on endpoint.
or on the endpoints. So when I check the endpoint, I would still scoop that up.
Okay.
Yeah,
Okay.
great question. I would still scoop that up. So let's go ahead and do this. We know that the critical numbers are x equals 0 and x equals, let's see here, we just did this one a second ago, and x equals 3. Notice that both of those are inside the domain from -1 to 32. Okay, so we're not restarting this question all over again. We didn't just take the derivative, set it equal to 0, find out where it's defined or where it's 0. We're just using our answer from before. So those are our critical numbers. And so now what do? We're going to go ahead and evaluate f of 0. We're going to evaluate f of 3. We're going to also evaluate what? We're also going to evaluate f of -1, and we're going to evaluate f of 32 as we go hunting for our absolute max and mins. Anyway, I'm now going to plug in these points. Why am I checking these first two in the first row? Because they're critical numbers. Why am I checking these two in the second row? There are endpoints. Don't forget to check your endpoints.
And just to clarify, we do this only when we're evaluating the absolute or global extreme, right?
This is our technique for finding the absolute or global extremum. Local extremum are something we're going to talk about after this unit. Okay, so if we plug 0 into this function, it spits out a 0. If we plug a 3 into this function, I'll give you the answer in just a minute. If we plug in a -1 into this function, it spits out a -9. And if we plug a 32 into this function, 2, 8, oh gosh, minus 192, I think. Yep. And if we plug a 3 into this function, it spits out approximately 9.67. So now we're ready to identify our absolute max and min. Okay, we've got the x equals x equals 3 is the location of the absolute max. And we've got the x equals 32 is the location of the absolute min. Why was that the location of the absolute max? Why is 3 the location of the absolute max? Because when I go looking at all of my y values, which one was the largest? Okay. And we say that the absolute min was at 32. Why? Because I go looking at all the y values that I tested, and that one was the smallest. Folks, how do I know that some other point on this function in this interval doesn't give me a higher value? Because it's a continuous function. The only way, if it's going upwards, if a continuous function is going upwards, how could it start going downwards to give me a maximum? It could either do it in a sharp manner, in which case the derivative would be what? Undefined. Or it could do it in a smooth manner, in which case the derivative would be 0. Either way, I would have picked it up when I searched for my critical numbers. So this is a very sophisticated way of narrowing down your choices to a small group of candidates, and then at the end of the day, you actually still have to do brute force on it. You still have to check some values. You plug them into the function and see what their y values are. Folks, do not plug 3, for instance here, do not plug 3 into the derivative. What are you going to get? You're either going to get 0 or undefined. How come? Because it's a critical number. You've already answered the question, what happens if you plug it into the derivative? You plug it back into the original function because you're looking for the height of the function. You're not looking for the rate of change of the function when you're saying, where's the tallest value on this function? I'm not asking what the rate of change is. I'm saying, what's the y value? So you plug 3 not into f prime, but into f. Okay, let's look at number 13 now. How is number 13 different from number 12?
The domain is different.
The domain is different. Okay, so we're still going to say that the EVT applies. In this case, I go to list the critical numbers. Oops, what? 3 is not a critical number in this more restricted domain. Now what do? I now test f of 0. I test, let's just do that for the first row. And I do f of -1, and I do f of 32. Well, none of those numbers have changed. Oops, why did I do 32? That should be f of what, folks? F of 1.
1.
The right endpoint. Oh, sorry, folks, I'm getting a little tired here. And if we plug in 1, I think it outputs a 7. So we see that x equals 1 is an absolute max. And x equals -1 is, let me be a bit more careful here. Let me say x equals 1 is the location of the absolute max. And x equals -1 is the location of the absolute min. So what you need to do now is you need to save these problems and rework them. Okay? Just write out the questions on scratch paper and rework the problems a few times until this becomes second nature to you. All right. I forgot about this one. All right. Let's see here. We'll do number 14 reasonably quick. Number 14 is another find the absolute max, absolute min problem. Okay. On some interval. Folks, there's going to be a messy factoring step in this problem. I hate to say it, but it's what you're stuck with. There aren't all that many functions where both the function factors nicely and the derivative factors nicely. There just aren't that many examples. Okay? This is one of them. I've scoured the land for others. I can't really find many others. Okay? So it means you're going to have to do a messy factoring step in the middle of this problem. So be it. That's life. All right? If you have trouble with factoring, please come by and see me. I would love to help you with it. Okay? But for right now, we're going to just have to say this is how this factors, and if you have questions, let me know. Okay, first of all, we're looking for a needle in the haystack. Well, f is continuous. Why is it continuous? It's a polynomial. F is continuous on a closed interval. So yes. That means that we know that we're going to find absolute extremum. Let's go find the derivative of this function. We need to figure out where is f prime undefined. And the answer is nowhere. It's defined everywhere. Then we need to ask where is f prime of x equal to 0? And the answer is when minus 5x to the fourth plus 28x cubed minus 36x squared equals 0. I just need to find the zeros of this fourth degree polynomial. That sounds a little bit bad, but it's not too bad because I can first factor out a minus x squared, and so I'm really just left with 5x squared minus 28x plus 36. Folks, everyone factors their own way. My way of factoring is I write out the pairs that multiply to 5, and I write out the pairs that multiply to 36. And I'm looking for a pair that add and subtract the right way. So this factors as 5x and x and 2 and 18 and minus and minus. Folks, I probably did that faster than you. That's okay. If you can't do it at all, you've got to come see me. So, this happens when minus x squared equals 0, or when 5x minus 18 equals 0, or when x minus 2 equals 0. That happens at x equals 0, or x equals 18/5, or x equals 2. So my critical numbers are, folks, go ahead and write out your critical numbers. What are our critical numbers for this problem? The critical numbers are x equals 0, x equals 2, and that's it. How come?
Because that evaluates to 3.6, which is outside of the domain.
Well said. So now what do? In our process of finding our global maximums and minimums, we're now going to plug in f of 0. We're going to evaluate that. We're going to plug in f of 2. We're going to evaluate that. I'm also going to plug in what, folks?
-1 and 3.
Points.
The endpoints, -1 and 3. Don't forget to check your endpoints. Okay? Folks, I still stand by the fact that I think you should be able to do my test without a calculator. I really don't want to plug a 3 into that function. Right? I don't want to take 3 to the 5th power and then multiply that by 7 times 3 to the 4th. Look what I did for you, folks. I gave you the function in factored form, which is a lot easier to evaluate these points at. So f of 0, if we plug in a 0 into this in factored form, or the other one, it's pretty quickly to see it's 0. For 2, that's a little bit harder. We'd have -2 cubed times 2 minus 4 times 2 minus 3. And if we do that, 2 and -1 is -2 and 8. 16. I think. Nope. That's -16, right? Nope, that's positive 16. Holy smokes. This guy needs to make up his mind. 16.
I think it's -16.
It's -16.
Yeah, I think it's, yeah.
All right. I'm getting tired. Got to get up pretty early if you want to make more mistakes than me.
-16.
Thank you, sir. Thank you. All right, let's plug in -1. So we get -1 cubed times -1 minus 4 times -1 minus 3. And if we do that, let's see here. That would be just a positive 1 times a -5 times a -4, which does come out to be a positive 20. This time I wrote it out. Nice thing is when we plug in 3, we get out a whopping 0. How come? Because x minus 3 is a factor, so that's not too bad. All right. Give me a thumbs up when you're caught up to here. Thank you, thank you. So I get that x equals 2 is the location of the absolute min, and that x equals -1 is the location of the absolute max. So moving down to question 19. It's called the mean value theorem. It's actually pretty nice. The word mean there actually means average. Right? You guys have heard that from statistics? The word mean means average. If you think about that, it helps you remember it. Okay? This is one of those theorems that I ask you to memorize. Okay? So this needs to go on a flashcard. And this is one of the few instances where I might say, state the mean value theorem on an exam. Okay? When I say state the mean value theorem, you can't just give me the part that I'm about to write in the blank below here. You need to state all of this. That's the mean value theorem. It's all the conditions and most critically what we call this is an existence theorem. So it's saying that something exists. So you do need to have all of that, and so let's go ahead and say, it says if the function is continuous on a closed bounded interval. That's the conditions to show that the what has to hold?
Extreme value.
The extreme value theorem. So we're saying, given that the extreme value theorem holds, and we know that the function's differentiable on the interior, that was related to one of the conditions of Rolle's theorem that we saw in our pre-work. Then there exists a C value. So this is what we call an existence theorem. It guarantees that a C value exists on the interior of this domain so that f prime of C equals f of B minus f of A all over B minus A. Da, 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 da. This is one of math people's favorite theorems in the whole wide world. You see why? That's pretty amazing. I don't see why it's so important. At least I didn't for a while. Okay? So if you're not impressed, that's okay. If you're not impressed, I understand. Let's talk about it though. Let's see if we can kind of suss out a little bit what's this saying. On the left-hand side, does that expression look familiar? Or excuse me, on the right-hand side, does this expression look familiar?
Slope.
That's the slope of what?
Secant line.
That's the slope of the secant line. In this case, of the endpoints. And one way to think about the slope of the secant line is that it computes the what rate of change?
Instantaneous?
No.
No.
Average?
It computes the average rate of change. For example, if I said I'm driving from Denver to Santa Fe, I cover the distance of 300 miles in 6 hours. If you do this formula, this slope formula, you would get an answer of 50. You'd say, oh, you averaged 50 miles per hour. That's how you compute an average rate of change. That doesn't mean that when I got in the car the whole time I was going exactly 50 miles per hour. Certainly not out of the FRCC parking lot. Okay? And certainly not on the interstate. But I averaged 50 miles per hour. Okay? What is on the left-hand side? What rate of change is on the left-hand side? Not the average rate of change.
Instantaneous.
On the left-hand side, we've got the instantaneous rate of change. So one way we can interpret this is that the mean value theorem says there guarantees to be a C value so that the instantaneous rate of change at x equals C, instantaneous rate of change matches the average rate of change. Yeah, that's okay. We're going to work on it here. I agree. I'm still not sure what I'm talking about. Let's keep working at it. Here's a physical interpretation of what we just said. If I tell you that your average rate of change was 50 miles per hour, again, think of me driving from Denver to Santa Fe, 300 miles, 6 hours. I averaged 50 miles per hour. The mean value theorem says as long as your motion is continuous and differentiable everywhere except at the endpoints, meaning I'm not jerking around as I go on the as I'm driving along, then there must have been a point in time where my actual speedometer reading was also 50 miles per hour. If I average 50 miles per hour, then at some instant I must have had an instantaneous rate of change of 50 miles per hour, as long as, and this is why you have to memorize it with the conditions, as long as the motion is continuous and differentiable. Then the mean value theorem holds. And again, in short, at some point in time, I mean, this is how I remember the mean value theorem. At some point in time, the instantaneous matches the average. Okay? Let's see what's going on here with the picture. Convince yourself of the mean value theorem. What we're going to do is let's go ahead and sketch a function. I'm going to sketch this function here. I'd like you to do one somewhat similar to me. There's the function f of x. Notice that the function that I drew is continuous. Drew without picking up my pencil. It's differentiable. I drew it without any jagged edges. So this function's continuous on the over the whole domain and differentiable on the interior. Now what? Well, if I were to go through and compute the average rate of change, the average rate of change is the slope of this line. How do you compute the slope of a line? With this slope formula right here, right? That's how you compute the slope of this blue line that I drew. Now, here it is, folks. The mean value theorem, if there's the way for you to understand it is to call it an existence theorem. It guarantees that a certain C value exists. I see it. Maybe you do too. I see that C value. I think that it's sitting right there. Give or take a millimeter. Why do I think that's the C value? Because if I go ahead and plot that point on the function, and then I sketch the tangent line right there, what is the slope of this tangent line? The instantaneous rate of change is the same as the average rate of change. Look at those two lines, the blue line and, as best I could draw it, the black line. Those two lines have parallel slopes. That's what the mean value theorem says. It says there's no way for you to draw a green function without having at least one place where the slope of the tangent line matches the average rate of change. Now, down here, nope, that's not it. That's way too steep. Down here, nope, that's not it. That's way too negative. But at that point right there, that point was guaranteed by the mean value theorem. Let's do it again. Let's draw maybe a little more complex of a function. Not too complex. It's still got to be continuous, meaning I can't pick up my pencil. And it's got to be differentiable, meaning I can't have any jagged edges in it. Then the mean value theorem says that there is at least one point where the slope of the tangent line is the same as the slope of that blue secant line. Can you find it? I see it. Do you? I think it's right there. Up to my ability.
Like, would there be a second one?
That's no problem, right? The mean value theorem doesn't restrict you to one. It just guarantees that there's one. In this case, as Daniel said, maybe others of you see it too, I think maybe right about there is a second C value. Both of them, if you were to evaluate the derivative at that C value, you would get what you calculated when you computed the slope of the secant line. Okay, folks, so let's look at this last example here. And now that we've got a better understanding for the mean value theorem, let's see if we can go ahead and put it to work for us. So we're asked to find the C value predicted by the mean value theorem for this particular function, f of x equals x cubed minus x, between the values a equals 0 and b equals 0. So we've got a nice graph here built for us, but let's hold off on using it for just a moment. So before we use that, what I'd like to do instead is let's go ahead and make sure, well, one, that we can apply the mean value theorem, and two, figure out how we're going to use this expression to help us out. So, one, notice that f is continuous. And here I'm going to do a little bit more than we need to. It's continuous on minus infinity to infinity, but so specifically on the interval from 0 to 2. So the fact that we're continuous on minus infinity to infinity is great. It's more than we need, but we do need to make sure that we are continuous on the interval for which we're working with the mean value theorem. Oops, excuse me. Okay, great. And then second, we notice that f is, where is f differentiable? Well, we can calculate the derivative of this function, and we will do so in just a second, but we'll notice that the derivative exists everywhere, so it's differentiable on minus infinity to infinity. Again, that's more than we need. Specifically, though, it absolutely needs to be satisfied that we are differentiable on the interior of this interval. So this is more than we need. This, you know, the fact that it's everywhere differentiable is wonderful, but this for sure has to be met for us to be sure that the mean value theorem is going to apply. Meaning, we're able to find a place where the instantaneous rate of change equals the average rate of change. So let's first go find the average rate of change, and we're going to do that by computing f of b minus f of a all over b minus a. Well, in our case, our function is the x cubed minus x, and that's our function, and we're doing this on the interval from 0 to 2, so we've got is f of 2, what is f of 2 minus f of 0 all over 2 minus 0. If we continue to compute that, we would have, so if I plug in 2 into this function, notice I would get out a 6. If I evaluated this function at 2, it would output a 6, so we get 6 minus, and if we plug in a 0 into this function, it would output a 0, all over 2 minus 0, and so we get a value here of 3. Great. So that's the average rate of change. And what would be the instantaneous rate of change? Well, if we find the derivative of this function, the derivative of this function is 3x squared minus 1. That's our formula for the instantaneous rate of change, right? For the instantaneous rate of change. So what I'd like to do now is let's set the instantaneous rate of change formula equal to the average rate of change that we computed. So let's do that now. So we're going to set 3x squared minus 1 equal to 3, and let's solve for x. So this happens when x squared, or 3x squared is equal to 4, or when x squared is equal to 4/3, or when x is equal to plus or minus the square root of 4/3, or if you like, plus or minus 2 over the square root of 3, depending on how you wish to write this. Only one of these two x values that we found is inside 0, 2. So the c value is 2 over the square root of 3. And that's because we had two of these, we had the negative value and the positive value. The negative value is not inside the interval 0 to 2, but the positive value is, so we'd say that's the c value. This on the interval from 0 to 2. Right. Okay, I want to highlight where on earth did the mean value theorem come into play, right? I mean, yeah, we checked the conditions that were met, but where actually did the mean value theorem show up? And it has to do with right here. What have we done at this point? At this point right here, I have set the average rate of change of 3 equal to the instantaneous rate of change. Now, once I do that, I have an equation In this case, it's a quadratic equation, and we've seen plenty of quadratic equations that don't have solutions. You know, for any given quadratic equation out there, there's nothing that says it has to have a real valued solution. However, I went ahead and solved this equation without any fear that we'd be able to find a solution. Not only would we be able to find solutions, but there would for sure be a solution on our interval from 0 to 2, and sure enough, that's what we found. So the mean value theorem guarantees that this equation right here has a solution. That was by the mean value theorem that we're trying to employ here. Okay. So let's go see how this all came into play on our graph. Okay. So here was the interval that we were asked to deal with. We were asked to deal with the interval between x equals 0 and x equals 2. And we say that when the mean value theorem applies, that there is a point on the interior of this interval, some c value, where the instantaneous rate of change, that is the slope of the tangent line at that point, agrees with the slope of the secant line connecting the two endpoints. So let's first draw the secant line connecting the two endpoints. So I'm going to put, there was the ordered pair 0, 0, and there was the ordered pair 2, 6. So we've calculated that point 2, 6. We calculated the point 0, 0, and then we found, this is the secant line, and we found that the slope of the secant line here was 3. The slope of the average rate of change, that is the slope of the line connecting the two endpoints, came out to be 3. Now, what are we looking for? Well, we said that we are looking for a point on the curve where the instantaneous rate of change matches that average rate of change. And I think that if I'm just looking at the curve, forget about our answer for just a second, I think that it looks to me like maybe our answer is right about here. Sure enough, if I draw the tangent line to the curve at that point, notice it looks like that slope is 3. And where is that point? Well, we just discovered that that was at the that had the x-coordinate of 2 over square root of 3, and then we would just find the corresponding y value by plugging that x-coordinate into the function. So this value right here, this is the c value predicted by the mean value theorem, and that was right there at 2 over the square root of 3. Again, the mean value theorem guarantees that that somewhere on this interval for the graph of this blue function here, there is a place on this curve where the slope of the tangent line is exactly the same as the slope of this red secant line connecting the two endpoints. And that's what the mean value theorem guaranteed for us. Now, to know that the mean value theorem applied, do make sure you do have to check those two conditions. That was part of the requirement for this to happen. And in fact, if f is not continuous, or if f is not differentiable on the interior, then the mean value theorem will fail on us. Okay, folks, that completes this lesson. There are certainly more problems to work in here, and I encourage you to go ahead and do so, and let me know if you have any questions. Thank you very much.